Hi guys, this is a lecture about alternating current and power. So it's 25.4 in the book, and this is really leading on to what is root mean square, RMS really, and where does that come from? And that's all a bit confusing really. So, what is RMS is what we're getting on to. And how do we get that, and why is it important? So from 25.3, which was the alternating current generator, which a lot of you've looked at, and I think we did cover a little bit in class, which is where we had the rotating coil in a magnetic field, and that was governed by a sine curve. But now we want to look at the alternating current and kind of what that really looks like. So, just a quick, brief recap. So, what is AC? So, AC is alternating current, and if I was to draw a graph of voltage against time, we would get something like this. And if we had an oscilloscope, then I would be able to show you, but unfortunately I can't. Now, so in the UK, I believe that's 325. You might hear words such as peak to peak value of the voltage. So, for example, if that's minus 325 value, minus 325, the peak would be 325, but the peak to peak would then be 650. Because it's going from plus 325 to minus 325, so it's going through a value of 650. So the red there is the peak to peak. Now, what is RMS and what's that all about? Now, the way we think about that is we want to look at the heating effect of an alternating current. Okay, so if we look at the heating effect, so what do I mean by that? Well, we've got a voltage and we've got a current. So you'll recall from your work on electricity in first year that P equals IV, which equals I squared R. Where R is the resistance of the heater element. So, say for example, if we had an electric heater supplied with this alternating current, and say that this alternating current was going at a really low frequency, right? So say it was kind of going really slowly like this. Obviously, we know that in the UK it goes at 50 hertz, right? So really, I should have put 325 and then 50 hertz right up here. That's what it is in the UK, but for the purpose of this demonstration, imagine that it's, I don't know, really, really slow. I don't know, maybe once every 2 seconds. So what's that? 0.5 hertz. Now imagine if that was the case. The heater would heat up and then cool down, heat up and cool down, and it would repeatedly heat up and cool down. So what power is being given and then lost? And that's I squared R. So the current is really, really important here. Now, so what's the peak? How can we determine the peak power supplied and this power supplied here? Where if this is the power and this is the time. So let's denote I naught as the peak current. So if we say I naught is the peak current, which would be the current at the top here. So I naught would be the peak current. So then we have at peak current I naught, max power would be equal to I naught squared R. And at zero current, zero power supplied. So, for a sinusoidal current, this is the key part, for a sinusoidal current, mean power over a full cycle, that's over one wavelength, is half of the peak power. So for a sinusoidal current, the mean power over a full cycle is half the peak power. So, therefore, the mean power given to this heater would be equal to I naught squared R over 2. So that's the mean power given. Now, here's where RMS comes in. The direct current so the DC value of current that would give the same power as the AC, which is, in this case, the mean power. So the direct current that would give the same power as the AC is called RMS. and it's denoted IRMS. So the direct current DC will give the same power as the AC, mean power, called the RMS. So what equation can we write here? So we can say the DC current that will give the same power as the AC is called the RMS. So we've got the I RMS squared times the resistor times the resistance equals the mean power from AC. So I naught squared R over 2. And we can just cancel these off, the R's off, which will leave us with I RMS squared equals I naught squared over 2. So the RMS current is equal to 1 over the square root of 2 I naught. I've just square rooted both sides here. That's all I've done. Square root both sides. But don't forget, I naught was our maximum current. So if I go and draw my graph again, and this value here is I naught, if I divide that by root 2, somewhere down here, that's the value of current that I would need to give the same heating effect as the AC gives. So that, if that was I naught, that would be my IRMS. Okay. So in the same way that we've got the current relationship, and because V equals IR, and R is a constant here, we can also say that V RMS is equal to 1 over root 2 V naught as well. So, and the last thing I need to say about this is, if you know the resistance in an alternating circuit, so for any resistor of known resistance in an alternating circuit, if you know the RMS, PD, or the current, you can calculate the mean power supplied to it. So the power would be the RMS current times R, if you know the resistance, which would equal V squared over R, which equals IR. So these equations still hold, even though we're in RMS. So this has been a little short lecture on what the RMS value means and how we calculate it. So it's not too complicated. It just means what is the value of current that I would need to give the same heating effect if I was in DC rather than AC.